Okay, welcome back to Engineering 5213, Tools of Operations Research, Lecture 5. This is Part 3. We'll pick up where we left off with Part 2, talking about network optimization models. We were looking at a network optimization that had a yield, in this case an oil refinery problem. It's shown here on the screen. I did find my mistake. There was a mistake in some of the numbers. It's difficult to explain now. It was easier, I found, to represent some of the constraints slightly differently. So I have the same first 6 constraints that we had before. The next few constraints I changed. So I wanted to change the constraint to represent that how you blend distillate and catalytic together to make regular gasoline as a single constraint. So for every gallon of distillate used to make regular gasoline, you need at least 1 gallon, or you need exactly 1 gallon of catalytic used. So those two numbers must be equal. So if we multiply 1 by -1, 1 by 1, add them up, that would be constrained to be 0. And then from there, so that represents how you blend distillate and catalytic together to make gasoline, regular gasoline. Then we can control how much regular gasoline can be made. And you could either do this by saying, well, for every barrel of catalytic, you'll make 2 barrels of regular, okay? Which means, so if you take your catalytic regular field here, the amount of catalytic used to make regular gasoline, multiply it by -2, and add that to the number of gallons of regular gasoline, that should sum to 0. You could have easily changed that, instead of being this field, to you do the same thing for the amount of distillate used to make regular gasoline. Because again, those two things have to be equal according to the constraint above. So that controls how much regular gasoline can be made and how distillate and catalytic get blended together to make it. And then similarly for the premium gasoline, we wanted to control first how catalytic and distillate get blended together to make premium gasoline. So in this case, for every gallon of distillate, if you multiply that by -3 and add that to each gallon of catalytic, those should sum to 0. That just means that we need 3 times more catalytic than we do distillate, okay, to make premium gasoline. And then again, for every 3 gallons of catalytic we use and 1 gallon of distillate, we'll make 4 gallons of premium gasoline. So I represented that here as 3 times the number of premium gasoline barrels should be equal to 4 times the number of catalytic barrels. Or we could have just simply made that 4 times the number of premium barrels is equal to 1 times the number of distillate used. And again, we can make that way because we've already controlled the blend of how distillate and catalytic have to be combined together for making premium gasoline in the constraint above. So once I corrected those two issues and correctly represented how regular and premium gasoline are blended by distillate and catalytic, and then how many gallons you can make, I was able to create an optimal solution here that you can see. So we decided to use in the optimal solution 49,333 barrels of crude oil. That gets broken into 29,600 barrels of distillate, 19,000 plus barrels of low-end product. The distillate then gets split into some number of barrels used as input to the catalytic cracking process, some used in distillate regular, some used as distillate to make premium gasoline. And so those all add up to, so these 3 columns here should add up to the amount of distillate barrels. So 20,000 plus 9,600 is 29,600. And then so forth. So that catalytic process produces some high-end product that we can sell, and some catalytic, which must be equal to the amount of catalytic we use to make both regular and premium gasoline. And then that, combined with the distillate used, controls how much regular and premium gasoline we can make and sell for a profit, subject to, obviously, their demands. So if you'll look here, scrolled over slightly, we can see what we're not using the full capacity of the tower. That is, we could have had more barrels of crude oil brought in and processed. The reason why we didn't bring in more, obviously, is because we actually hit two different constraints as binding. One is the catalytic process couldn't handle any more barrels. That is, we couldn't have made any more catalytic, any more high-end byproduct. So there was no point in bringing in more crude oil because we couldn't use it properly through our catalytic cracking process to make any more product. Okay. Likewise, we produced all the regular gasoline that can be sold. That is, we produced the 16,000 barrels of regular gasoline that we thought we could sell, even though that did also mean we did produce less premium gasoline, which is more expensive, could be sold for more than the market could bear. But these two conditions combined, the catalytic cracking process capacity and the demand capacity for selling regular gasoline, both formed a binding constraint that limited how much of our process we'd utilize, forcing us to use less crude oil than technically the tower could handle, but for a maximum and optimal profit of $466,000 roughly. So that's a network model with a yield. You can imagine other network models. You can represent every network model using a diagram, circles and arcs or circles and edges. And it's useful to do that to help visualize and understand how the network model is going to be put together. Network models can either be in the form that we looked at early on, like this, where we use a grid, where the network is symmetric. That is, there's a number of sources, a number of destinations, and every source-destination pair is a possibility that we can use to either ship something or assign something or assign some amount of flow that's going to flow from that source to that destination. But we also saw where in some network optimization problems, such as this one here with recycled paper, or the one we just looked at with oil refineries, the network is not symmetric. There's not a set number of sources that can all flow to a set number of destinations. So it's a complex flow that involves some edges that don't exist or some edges that don't flow from one particular source to one particular destination, or there's multiple intermediate destinations in between, and it's easier to represent those in this row-based form where we represent each flow between one node to another in the network as a different column, and then assign values in a row of how much flow, how much product, how much information, how much in one case oil product, or in this case paper product, is going to flow from that input to that destination, or from that source node to that destination node. And then our constraints are represented simply by some products, where we multiply some values times some of our decisions, and then constrain those values summed up to be less than or equal to, or in some cases strictly equal to, in this case of the oil refinery, strictly equal to something like 0. So that takes care of network optimizations. We're going to move on from there and talk about integer optimizations. So we talked about covering problems, assignment problems. We've talked about network optimization problems. All of those are linear optimizations. And now we're going to talk about another class of linear optimization called integer. Integer optimizations are essentially the same as the regular linear optimizations we've been looking at, except that we're going to also constrain the decision variable values to be integer or whole numbers. So in some problems, like the assignment problem we looked at in the past few parts of Lecture 5, we were assigning swimmers to swim different strokes of a relay team, and because the demands and capacities of that network problem essentially worked out to be 1, it forced that all our decisions be either 0 or 1, because it wouldn't make sense to have somebody swim half a stroke along with somebody else swimming half that stroke. Somebody is obviously going to be faster, so it's optimal always to assign a full person to a full stroke in the case of that swimming exercise or that swimming example. Other problems, however, don't necessarily lend themselves to only integer decision variables or decision values, but we might want to constrain the problem in that way and say that it only makes sense to either be a whole number, or in some cases may only make sense to be 0 and 1, binary numbers, for our decisions. So for example, let's think back to the furniture production example we used in the last lecture, lecture number 4. And I have a sheet representing that here. So if you remember, there were 3 kinds of furniture that our company could make: chairs, desks, and tables. Each product could be sold per unit for some profit. We had 3 different departments involved in making our furniture: for fabrication, assembly, and shipping. And those departments required different number of hours to produce each different furniture product, chairs, desks, and tables. And each of those departments had a capacity, number of hours they could work. And then finally there was a demand, a market demand, that said how much of each furniture type we could sell. So here we had chairs, desks, and tables. I've already solved this with a simple linear model to suggest that we would make 275 desks and 100 tables, 100 tables being the maximum amount of tables we could sell. And so that's a binding constraint, as you'll see here. But we don't make all the desks we could sell simply because to make the 275 desks and 100 tables requires all of the hours of fabrication department that it has available. So that's another binding constraint preventing us from finding a better profit by making more product of any kind. Okay. Now we also looked at a optimization sensitivity form of this problem, where we said, what if the fabrication hours, the fabrication department hours were increased or decreased, and how would that affect the solution? So I want to show just one quick example. Let's imagine that the fabrication hours were reduced to 1800 instead of 1850, and we resolve the linear optimization problem. Here you see that because the fabrication department only has 1800 hours available, that's still going to be a binding constraint, binding our optimal solution. However, now the optimal solution is to produce 100 tables and 266 2/3 desks. Obviously, it doesn't make sense to produce 2/3 of a desk. Now, in the real world, a simple model like this, you might just round and say, let's just make 266 or 267 or something like that. But in some problems, we might actually be forced to say that we can only assign whole numbers, integer numbers, to each of our decision variables. And so, using this as an example, let me show you how that's done. If we want to constrain our decision variables to only be whole numbers or integers, we're going to do that with an extra constraint. So I'm going to highlight the decision variables here, go to the constraints. In this case, we're going to use a normal constraint, although these 3 options aren't really all the options available. So if you just select any one of them, and it brings up the add constraint dialog, you'll see that right now it's asking me which value or cells should B3 through D3 be less than or equal to. However, that less than or equal to is a drop-down that has other options. For example, we might choose an option to say int, which is each value assigned to B3 through D3 must be an integer, must be a whole number, and that's what we want. And so now we don't have to specify a value or a cell to reference. We're just simply saying these values can only be whole numbers. They can only be integers. That's a constraint of the problem now. So adding that constraint, I can now rerun the integer optimization algorithm, and now it has found that the optimal profit, still subject to the constraint of the fabrication department, and in this case the table demand, is to make 100 tables, 266 desks, but with that 2/3 of a desk not being made, we can now afford in the fabrication department to make 1 chair, which yields a better profit than if we had not made that chair, obviously. So making a chair that we can sell for $15 increases profit by $15. And we've now constrained the problem to be only integer solution, or only integer values for our decision variables. Again, we did that with a constraint. If you look on the model tab, you'll see, as we've seen before, the objective, the decision variables, and some constraints listed. But if you scroll down, there's now a new constraint type that we hadn't seen before, which is the integers constraint, simply to say B3, C3, D3. Cells in those ranges must be equal to integer, must have integer values, let's say. All right. So that's integer optimization. Let's do another quick example of that. So one other kind of example that we might look at is not just enforcing that whole numbers be used, but in some cases we might actually want a binary decision, that is a yes or a no, a 0 or a 1. Sort of like the example we saw of the assignment, where we are assigning swimmers to swim different strokes of a relay team. We might want to sort of decide either we want to do something or don't want to do something. We can't half do it, we can't do it a fractional amount, we can't do it more than once, and we can't do it less than 0 times. So that would be a case of integer programming or integer optimization, in which case the integers really are binary values, one of 2 options. So for example, let's imagine a company that has 5 potential research and development projects that they can invest in. Now each one comes with a projected net present value, that is how much worth that project has. So we'll call that NPV, net present value. But they each come with some investment cost, that is we have to invest some money to pay people to work on those projects. Even though they'll give us a profit, a net projected value in the end, they still have to be paid for. We have to pay for somebody to do them. And we have a budget, a limit to how much we can invest in such things. So for example, as a simple example, imagine we had 5 projects that we could invest in. We have a known amount of net present value for each one that we want to maximize. So we want to choose projects to maximize net present value of the selected projects. But we have to do so subject to limits of the expenses, the budget constraints that each project comes with. So for example, a budget of 160, let's say these are millions of dollars, $160 million, we can't choose all 5 projects to work on because that would be more than our budget. So which projects should we choose? So obviously we're choosing to do something or not. These are binary decisions. We either choose project 1 or we don't. We either choose project 2 or we don't. So let's look at those values and create a Excel spreadsheet to work with this model. So here we have our projects, project 1, 2, 3, 4, and 5. Each has a net present value and each has an expense. So the net present values are 10, 17, 16, 8, and 14. And again, let's assume maybe these are millions of dollars, thousands of dollars or something. And then they each have an expense, that is how much we have to invest in them in order to get that profit, in order to get that much value plus the net present value back out again. So these currency values. We're going to decide on these things, okay? So we'll make a row to represent our decision variables. And then we have an objective, which is the sum product of the net present values by which projects we decided to do. So by using binary numbers, zeros and ones, we can either choose to do a project, in which case we'll assign a 1 to the decision variable, in which case we multiply 1 by the net present value, or we can decide not to do a project, in which case we use 0 to represent that. Multiplying 0 by the net present value is 0, and so the sum product works very nicely for us here. And that both is our objective and currency value that we want to display. So now we have essentially the decision variables and the objective computed. We also need the budget constraint represented, which will be the sum product of which projects we choose to do by their expenses, and that must be less than or equal to, in this case, 160 million. So let's format both of those as currency values as well. So we have our decision variables here. We have our objective that we want to maximize here. And we have our essentially only numeric constraint being the budget. Okay. Now if I solve this problem now, which I'll go ahead and do, what we'll find is it will decide to do fractional amounts of some of the projects. Now I do want to constrain it to be only positive values. So let's do that and see that obviously we should do project 5 2.96 times because it has the lowest expense for the net present value worth that we get out of it. And that perfectly uses the budget. However, that's not realistic. We can't do a project 2.96 times. We can only do it or not do it. So we need to constrain the decision variables again, like we did for integer optimization. We want to constrain these to be, in this case, not integers, but binary numbers. So this bin option here in the add constraint dialog will force that the values assigned to the decision variables are binary, a 0 or a 1. Nothing in between, nothing outside. So once we've added that constraint, we can resolve, and we find that the best solution is to do projects 1, 3, and 4. 1, 3, and 4 give a net present value, total net present value of $34 million, and it perfectly uses our budget. Now, this worked out nicely in that 48, 80, and 32 added up to our budget of 160. Under normal circumstances, you might not find that the budget or the expenses you have will perfectly add up to the budget, but there's no more projects that could be selected, okay, that would fit in the budget. That doesn't mean the budget is not constraining. It means that the combination of the budget and the constraint that you can only do a project or not, you can't half do or fractionally do any projects, those two constraints sort of together become binding in that you can't do one more project because of the budget, but you can't increase how much you spend closer to the budget without because you can't do partial amounts of a project. So those are the sort of binding constraints in tandem with one another. So this is a good example. So we have 5 projects. We've chosen to do 3 projects subject to not exceeding our budget and maximizing our net present value. Let's go back to the presentation. And there's a few more things we can talk about. That is, there are some special classes of constraints that we can have, especially in these binary optimization problems. For example, you might want to say something like, let's say we want at least one of project 2 and 5 done. So we've chosen not to do 2 and 5, but for some reason, let's assume that the company has decided they want to do at least one of those. Maybe both, but at least one of 2 and 5. And so we can represent that with a new kind of constraint. Okay, so I'm going to represent that as some general constraints down here. And what I'm going to do is I'm going to multiply using the standard form of multiplying our decision variables by some values here. I'm going to multiply project 2 and 5 by 1 and constrain that value be greater than or equal to 1, simply. So I'm just saying here that out of 2 and 5, you must choose one or more of them. Okay, so the sum of what you choose between 2 and 5 must be greater than or equal to 1. So let's add that as a new constraint. This value greater than or equal to this one. Oops. This one. And now let's recompute or re-optimize. So now the optimal solution is to do projects 1, 4, and 5. Okay, so we've met the general constraint, that is, we've done at least one of 2 and 5, projects 2 and 5. We're not technically meeting the budget constraint, that is, there's more budget that could have been spent. Now, there's no project which has a expense less than the budget we have left available. Okay, so obviously we couldn't do one of these projects because we didn't have the budget available. And again, we're maximizing our objective. So it was optimal, given that we had to choose at least one of project 2 and 5, it was optimal to choose to do projects 1, 4, and 5. Okay. But Let's imagine another kind of constraint that says you can do a mutually exclusive constraint. Okay, so one that would say if you do, or I'm sorry, you can't do projects 4 and 5 both. Okay, so for some reason those two things require some of the same person's time or some of the same resources, such that we can't do both project 4 and 5. So again, I'll represent that as a general constraint and say, if I multiply projects 4 and 5 by 1, whether or not we do 4 and 5 by 1, I'm going to constrain that to be less than or equal to 1, meaning you can't do any more than one of these two projects, projects 4 and 5. So let's add that now as a constraint. So this one is less than or equal to 1, and let's resolve. So where it was optimal to do projects 1, 4, and 5 for an objective of 32, now that we can't do projects 4 and 5 together, it's best for an objective of just 31 to do projects 2 and 5 only. Okay, so that's an interesting types of constraints that we can add to these kinds of problems. So the first was a constraint that said sort of a minimum, at least this many things must be decided on. So at least you have to do one of projects 2 and 5. And then beyond that, we added a new constraint saying you can't select more than one of projects 4 and 5. So you can't do both 4 and 5, but you have to do at least one of 5 and 2, and you have to do it all within a budget of $160,000. Okay. Let's add one more type of constraint that we'll call a contingency constraint. Okay, so a contingency constraint is going to say something like you can only do project 5 if you also do project 3. Okay, so doing 5 is contingent upon doing project 3. Now this one's a little more tricky to represent and a little less intuitive to think about. So for example, if we chose project 3, we could choose project 5. We wouldn't have to, but if we were doing project 3, we could do 5. However, if we don't do 3, we can't do 5. Okay, so I'm going to represent that here as a 1 and a negative 1. So for example, if we did project 3, we'd multiply that by 1 and get 1. So doing project 3 gets us a positive 1 on this row. But doing project 5 reduces that 1 back down. Okay, so again, we're going to use our standard sum product. Now this contingency relationship saying if you do 3, you must do 5. What we're going to do is we're going to constrain that to be greater than or equal to 0. Okay, so the only way this value can be less than 0 is if we don't do project 3, but we do project 5. Okay, so we don't do project 3, so that's a 0, but we do project 5, so that's a negative 1. So we're just going to constrain this to be greater than or equal to 0. We could do neither project, in which case it'd be 0 here. We could do project 3 without 5, in which case it'd be a 1 here. Or we could do project 3 and project 5, in which case we're back to 0 again. The only thing we can't do is 5 without 3. So this is a contingency type of constraint. So let me label these. We'll call this a at least constraint, a mutually exclusive constraint, excuse me, and a contingency constraint. So now let's resolve. So where it was previously optimal to do projects 2 and 5, now that we can't do 5 without 3, let's find out. Is the optimal solution to stop doing project 2 and start doing 3? Or is it to stop doing 5 in favor of something else? Oh, and I did not add that as a constraint. So that value must be greater than or equal to this one. Now we can solve. Okay, and it turns out the optimal solution in this case is to do projects 3 and 5. So it was better to do 3 so that we could do 5 than it was to stop doing 5 and continue to do 2 and maybe some other things. Out of just curiosity, so doing projects 2 and 5 yielded an objective of 30, as we see here. So if we didn't do 3, we couldn't do 5, but we might want to do 1, 2, and 4. Okay, well, we can't because of the budget constraint. So let's assume maybe we don't do 4. So we see, obviously, it was better to do 3 and 5 than just 1 and 2 because the objective is lower. However, maybe we could have done 2 and 3, okay, because again, we can do project 3 without 5. And in that case, we again violate the budget. So we can't do 2 and 3. So let's imagine then maybe we would do 2 and 4. Well, that's lower than our budget, but not a better objective. So obviously, it had the right idea by doing 2 and 5 to meet all the constraints. Okay, I'm sorry, 3 and 5. This was 3 and 5. To meet all the constraints, budget, and these other general constraints, and maximizing our objective. And this again was a binary optimization problem solely because we had in our model a special constraint that said our decision variables must be binary values. They must be 0 or 1, nothing in between, nothing outside. So we either do a project or we don't. We either pay the expense and receive the net present value in our objective, or we don't. There's one other kind of special constraint that I want to talk about, and then we'll be done for the lecture. And this special kind of constraint is called a linking constraint. So we just looked at least constraints and mutually exclusive constraints and contingency constraints. But there's another kind of constraint where we want to use binary optimization, so we either do something or we don't. But we also want to decide on how much of something we do. So we can do 0, we can not do something, in which case we may avoid paying some fixed costs. But if we choose to do it, we have to pay the fixed costs, and we can choose how much to do, in which case we also pay a variable cost. So this is called a linking constraint, in that we want to link together 2 different kinds of decisions. One is a decision whether we do something at all, and if we do decide to do it, another decision is how much of it to undertake, how much process to do, how much product to sell, or how many things to make, let's say. And again, there's both a fixed cost that we only pay if we make that decision to do it, and there is a variable cost which we pay on how much we decide to do. Now, the way we represent these linking constraints, so this binary decision and a variable decision, is using something like this. So if we imagine we have a fixed cost F and a variable cost C, okay, then we have 2 decisions. One is a binary decision, let's call it Y, of whether to do something. Now, we only pay the fixed cost when Y is 1. That is, Y is we decide to do it. So Y is 0 or 1. When Y is 1, we pay the fixed costs. So F times Y is the part of the fixed cost that we'd have to pay. If we decide not to do something, then Y would be 0, and F times Y would be 0. But there's a variable cost as well. Let's call the amount we decide to do X, and we would multiply that by the variable cost C. So Fy plus Cx is our total cost. Now, if we choose to do something, Y is 1, then X can be any value. We can choose how much to do. But what we want to do is link together Y and X by saying if Y is 0, that is, we decide not to pay the fixed costs, then X must be 0. That is, we can't do a little bit if we've decided not to do any at all. Okay? So we're going to represent that with a linking constraint, something like X is less than or equal to M times Y, where M is some arbitrarily large value. So this works out rather nicely because if Y is 0, M times Y is 0, which means X must be less than or equal to 0. Well, we'll constrain it to be positive, so it must be 0. It can't be anything less than 0. So X is 0 when Y is 0. If Y is 1, that is, we decide to undertake some process, then m times y is just m, some really large value, which just becomes an upper bound on x. If you have a capacity already in mind for x, so you can only do so much x, make so much product, sell so much product, then m just can be used as your capacity. And the linking constraint, x less than or equal to my, where m is capacity, serves both as a linking constraint, linking y and x decisions together, as well as the capacity constraint on x. So let's look at a quick example that does that. Let's imagine a company that produces 3 products, each requiring production hours in 3 different departments. Sounds a little bit like our a little bit like our chair, desk, and table furniture example. But in this case, we'll just assume 3 random products. Now, each product requires its own sales force. That is, the people we pay to go out and sell the product. Now, if we're going to make product, say product A, then we have to pay the salespeople, regardless of how much they sell. So the volume doesn't really matter. If we're going to make any at all to sell, then we have to pay the salespeople that fixed cost. So there's a fixed cost associated with paying the sales force. However, if we've decided to pay them and decided to let them sell, then the volume of what they sell also comes maybe with some variable cost. That is, there's a variable cost associated with how much it costs to produce each unit of the product. For example, let's consider these constraints or these parameters to our model here. So 3 products, P1, P2, P3, they each have a unit profit. They each need so many hours in 3 different departments, say department A, B, and C, and the amount of hours needed per 1,000 units of product is given in this lower part of the table. Now, each department has a capacity, number of hours available that they can work, and we have both a sales cost, so in terms of thousands of dollars, that is, if we decide to make product 1, we would need so many hours of A, B, and C departments' time, and we would also have to pay a fixed cost of $60,000. Okay, and for each unit of P1 we make and sell, then we can make a profit of $1.20. However, there's a demand or market cap that would say we can only sell 400,000 P1 products. Okay, so there's both a demand constraint, a capacity constraint on the departments, and a fixed cost, okay, associated with whether we produce the product at all. Now, the variable cost of the product, you can either consider that some of the variable cost is embedded inside the profit. That is, if we have to pay 80 cents for the materials, but we can sell it for $2, that's why we have a unit profit of $1.20. However, there's also some variable cost associated with the hours required in each department for making a P1 product. Okay, so those are the variable costs that we would have to pay for every unit of P1 we make. However, there's a fixed cost as well. So what we're going to have is 6 decision variables. 3 decision variables which are binary, which say whether or not we make product 1, product 2, and product 3. And then 3 decision variables which are how much of P1, P2, and P3 to make, subject to obviously using less than 2,000 hours of all 3 departments and making no more than the demand of what we can sell. So let's look at how we remake that Excel sheet. So again, let's assume we have product P1, P1, P2, and P3. Okay, and we're going to decide whether we make them, and then we're going to decide basically how much we make, okay, of each product. So those are going to be our 6 decision variables. So we'll color those in, maybe even put a border around them. Okay. So let's say we don't decide to make any of them, in which case, right, we can't make any. Now, there's a profit associated with each one. So $1.20, $1.80, and $2.20, And obviously we'll use our standard sum product to say for every one we make multiplied by the product, multiplied by the unit profit will give us a dollar amount of how much profit we'll make. Okay, so that'll be our objective, similar to many other problems we solve. And now we have our constraints. So first we have constraints on Department A, Department B, and Department C hours that get used. Okay. So for example, Department A requires 3 hours, 4 hours, and 8 hours, respectively, for 1,000 units of product P1, P2, and P3. So we'll again use sum product. These are based on how much of the products we're making in terms of thousands of units. So we may remind ourselves that those are in thousands of units, and that has to be less than or equal to 2,000 hours. Okay, and similarly for Department B and Department C, so those are the department constraints. There's also demand constraints. So there's only a demand for 400,000 units of product P1, only a demand of 300,000 units of product P2, and only a demand of 50,000 units of P3. Okay. And then finally, we need our linking constraints. Okay. So our linking constraints are going to say something like our linking constraints say something like the x value, or the how much variable here, must be less than or equal to some maximum multiplied by the decision variable. Now again, I told you can incorporate those into your capacities if you're clever about it. Okay, so let's try to do that actually. So instead of representing a separate constraint, let's say the demand of P1, well, it isn't just 1 times that. This is actually, let's see, that's correct. 1 times how much has to be less than or equal to not 400, but whether or not we do it, times 400. Okay. So again, the linking constraint says the x, the variable, decision variable, must be less than or equal to the binary decision variable times some maximum value, some capacity. Okay. And similarly here, so whether we do P2 times 300 and whether we do P3 times 50 form the linking constraints that say this value can be 0 if this one is 0, but this value has to be less than or equal to this one times some maximum capacity. Okay. So the last thing we didn't account for is not just profit, but fixed costs. So in this case, we had fixed costs of 600, 200, and 100,000. And those are going to get multiplied by the decision variables. Okay. And our objective now really isn't those any one of those two things, it's the sum of the two. So the amount of profit we make minus, sorry, not the sum, the amount of profit we make minus the costs, the fixed costs. Okay. That is now our objective. Okay, so let's go ahead and define the model. So these are decision variables. Go ahead and define that our decision variables for deciding whether or not to make each product are going to be constrained to be binary. Okay. This is the objective that we want to maximize. And these 6 constraints down here, all being less than or equal to, form really 9 different constraints. That is the capacity of departments, the raw demand of the market, and the linking constraints between each decision and how much to make of each product. So let's run the model. And what we found was we should not make product 3. We should only make product 1 and 2, and we should make as much product 1 as technically its demand will allow for. So if we used our standard test here to say if this value is greater than or equal to that one, this is a binding constraint. Otherwise, it is not a binding constraint. So our demand on P1 is binding. Okay, and the other binding variable really is the department B hours. That is, we made all of product 1 that we could sell and enough of product 2 that we used all of department B's capacity. Now, the other binding constraint is the demand of P3 because the demand is technically 0 if we don't make it. Right? So that's our linking constraint combined with the capacity. So this binding constraint here is really the linking constraint is binding. That is, the linking constraint enforced that this must have been 0 in order, because this was 0. Because we didn't decide to make product 3, we couldn't decide how much to make. That is, we had to make 0. And of course, our maximal profit in this case was $508,000. Okay, that should take care of it. We could use optimization sensitivity to examine some possibilities. So we might say how much of department B's hours should we try to increase in order to make a better profit. And so we could say something like, let's use the PSI op param, say anywhere from 2,000 to 3,000 hours might be useful. Okay, so this parameter here, the number of department B hours, is set equal to PSI op param, which says will vary from 2,000 to 3,000. And then let's go ahead and name some of our cells. So we'll call this make P1. We'll call this one make P2. We'll call this one make P3. Just name that one P1. Oops. We'll just call it 1. Oh, that's not going to work either. P1 amount. Call this P2 amount. And we'll call this one P3 amount. And then we'll call this the net profit. And let's go ahead and name some of these other cells. So we'll call this department A. We'll call this department B. And we'll call this department C. And now we can run an optimization sensitivity report to say, let's do 11 points using I3. I'm sorry. This is now in J12. Objective is profit. And let's just go ahead and we're interested in all possible decisions. So we'll generate that report and say, if department B's hours was increased from 2,000 up to 3,000 in increments of 100, okay, at what point would we make a different decision? So up till so for every 100 hours of increase, we decided to make more P2. Okay, so we can make more P2 up to a point at which we decided, interestingly, that with more hours in department B, right? Some other department likely became binding, which means we could make more P2, but it was better to make more P2 and less P1 for a better net profit. Okay, so we got a net profit of 600,000 for every Department B hours from 2,300 up. Okay, by making lots of P2. In fact, if we go back and look, the P2 demand is 300. Okay, so make the maximum amount of P2 using Department B's long hours now, and make some fractional amount of P1 that's only the amount of hours left, likely after. So if we just say this was 2,300 and we solve, so let's see what becomes binding. So Department B's hours are still binding, but now Department A's hours are becoming binding. So the more we add to this, obviously, we're not going to get any better of a solution because Department A can't make any more product. So that's using optimization sensitivity like we have before to answer that kind of a question of if something in the model changed, some parameter was adjusted, how would the optimal solution change? What decisions would be made differently for a better objective given changes in some of the parameters? That takes care of linear optimization. So we've spent roughly 3 weeks talking about it. We've done some by hand. We've done some simple problems, assigning and coverage models. We've talked about network optimization models, which we use diagrams to represent. We moved to different types of network optimization: transportation, assignment models, transshipment models, and then models, network models where yields were involved. That is, the amount going into a node is not necessarily equal to the amount going out. The amount out may be more or less than what comes in. And then we looked at integer optimization by constraining decision variables to be integers only, and binary programming or binary optimization, in which we have decisions that are limited to only the value of 0 and 1. Binary meaning yes or no, true or false, 0 or 1, we do something or don't do it. So in this case, we ended with, in fact, a linear optimization problem that involves some binary decision variables and some non-binary decision variables, but they were linked in some way that said the binary decision variable forms a capacity or forms a limit or upper bound on the variable decision variable. So we can only produce P3, we can only decide how much to produce if we decide to produce it at all, and we need to know whether we produce it at all to know whether or not we can pay the fixed costs. So in this case, again, we're only going to hire and pay salespeople for selling product P1 and P2, not hiring anybody to sell P3 to avoid paying the fixed costs associated with that, even though, in this case, P3 technically sells for more profit per unit, but obviously also requires more hours in the departments to make. So it was better to use the department's hours to make combinations of P2 and P1, as many as we could, up to some demands, up to some department constraints, and pay those fixed costs in order for getting some amount of profit even greater, so that we can net a profit, in this case, of 600,000. That concludes Lecture 5. That concludes linear programming. Next lecture, lecture number 6, we will start talking about nonlinear and non-smooth optimization models, followed by talking about simulation and optimization and simulating models before the class is concluded. Thank you very much for your time.